All right, want to finish up as is appropriate, given it's raining out now. Right now, I wanted to thank you. Wanted to finish up going over the last flavor of flooding. Remember last time we talked about riverine or quote unquote regular, normal quote unquote flooding, right? And we said before that that's in contrast to what happens immediately along the coastal fringe. And so just wanted to go over that with us. Okay, so let's talk about coastal flooding. I mean, obviously, in the big picture of water going from wherever the normal level of water that we expect it to be to higher, that's kind of similar, but there's some important differences here. So as we mentioned before, we have the regular flood or stream or riparian flooding. Also technically can be lacustrine flooding, but we're not really around lakes very often. And then coastal flooding. And so the major drivers, as a reminder, of the stream flood are rain. And so typically we see that this tends to be a fairly seasonal activity when that sort of storm season hits or when snow pack melts, right? So it's a fairly predictable phenomenon. Yeah. Okay. So for coastal flooding, it's a bit different. Obviously, storms can play a role as well. So we could have a big storm roll out of the Pacific and towards us in California that can induce coastal flooding. And so most typically, for us, our largest storms of the year are winter storms. If we're in Florida or the Carolinas, that's going to be more hurricane, sort of summer hurricane season. But for us in our part of the world, it's typically winter storms. Particularly winter storms when the tide is particularly high. So for those of you that haven't taken coastal yet, or maybe haven't taken physical oceanography yet, we have what's known as a semi-diurnal tide. So that means we have, on most days, 2 highs and 2 lows. And one of the highs is higher than the other, and one of the lows is higher than the other low. So they're kind of a mixed bag here. And so that goes on every day. So every day we have some high tide, every day we have some low tide. But then over a seasonal cycle, over the month and everything, we actually can get, that elevation of that tide is going to change. And so for the seasonal highest of the high tides and lowest of the low tides, we call those king tides. And so the king tides are where the ocean, even with no storm and no wind and no nothing, is just going to be unusually high. And if we have a storm that hits at that particular point, that's where we see the most problematic coastal flooding. And obviously another big driver of this, kind of for our part of the world, but really we don't get that many cyclonic storms hitting us. We get a few, but in other parts of the world where we do have of typhoons and hurricanes, etc., it's really going to be the summer and early fall that they'll see the most coastal flooding. Oops. Right, and just like everything else, we have the basic physics of the atmosphere going on, and then we have the stuff that we are doing to the environment, making things more vulnerable to flooding. So the meteorological stuff is going to include that rainfall. It's going to include warming of the warming season that tends to have rivers swell, that kind of stuff. And then the anthropogenic drivers are the things that we are doing to make the landscape more floodable, right? Either put ourselves in greater risk or make it less likely for, say, that water to go into the soil, that kind of stuff. Okay, so one of the biggest issues here that's changing the flood probability in the coastal zone is obviously global sea level rise. And so that's what we're showing here. And so this is data from NOAA. Unclear how much longer you'll be able to see this because there's active efforts to pull all this information down and make it more obscure, if not outright hide it from you. But this is the real data. This is the real reality of the world. And so in this case, we're going into the 90s to recent times, and we're going from 0 centimeter elevation above background to up to 10 centimeters. So historically, we did this by literally putting a stick in the water or putting a mark on a rock or something like that, and just going out every day or every hour or whatever and checking it. We call that a manual gauge or a manual tide gauge. And so we did that for a long time. Now we have more sophisticated things that a person doesn't need to physically be there. We can record it, we can log it. And also, starting in the wake of World War II, and the birth of the satellite era, when we started launching satellites, now we have pretty darn sophisticated satellites that can get very fine resolution measurements of the height of the ocean. And that is key for global models, because no longer do we just need to rely on you or me walking down to the pier in a handful of locations along California, but we can get huge swaths of the ocean surface and areas near where people are not, next to the coast, far from the coast, all those kinds of things. So it's a much more robust data set. And that's what you're seeing with the black lines. Okay, and then what we're looking at here are other estimates. So that's the story. So the big story is the black thing, right? It started off down there and it's getting up higher. Now, as with all of our data, there is some ups, there is some down. There is some noise, right? It's a natural system. But this is the long-term average. And what we're seeing here is there's a couple different components. So the water is the average. If we put a ruler and jammed it in the, really deeply down through the sand, down to the bedrock, so it wasn't moving around with the sand or whatever, and came and started checking it, we're several centimeters higher than we have been in past decades, right? The sort of long-term average. The other thing I need to say before we go into this is to remind you guys that the sea level has always been fluctuating. It's never static forever, right? Some seasons or some eras it's gone up, some eras it's gone down, right? The Channel Islands, so as far as we can tell, the Channel Islands were never physically, in their modern form, were never physically attached to the mainland, but they were very, very close. They were more like, how did those mammoths get out to the Channel Islands? Somebody swam, it's true, that's what we currently think at least, but they had to swim like a mile or two. They didn't have to swim 17 miles to get out there, right? So the sea level has fluctuated up and down, and that is real. That has always gone on because of changing overall climate. This is basically all people. This is all us. So we are layering on top of the background story of if no humans were on planet Earth, sea level rise. Okay, so and now because we've done all this kind of stuff, we actually are getting pretty good at modeling this, pretty good at both predicting how it changed in the past, and therefore, once we get that model super good by modeling with historic data, we can then pivot around and point forward and predict what's going to go on in the future, making some certain assumptions about how much CO2 is in the atmosphere and some things like that. And so basically what we see is this first thing that's driving sea level rise is thermal expansion. So if we just take water and in this room and we increase the temperature, the water is still going to say water, but it's going to tend to be a little bit more, the molecules a little more rubbing, kind of bouncing, and that's going to tend to make it expand just slightly, right? And if it's in my little glass of water, we wouldn't be able to tell that, right? And if it's in a tub of water the size of this classroom, we wouldn't really be able to tell that. And if it's in a swimming pool, we wouldn't be able to probably tell that, right? But when we get to the scale of the Earth, even just a little teeny bit of less dense molecules together actually can lead to some difference. And so that's what the change from the elevation in the red is due to that more heat being held by the ocean body itself. And then we're actually adding more water into the ocean. So did anybody, maybe somebody post about this, did anybody post about what just washed up on South Georgia Island last night or the other day? Anybody post about that? So a glacier, a chunk of the sea ice, not the sea ice, sorry, no, it was glacial ice. So that was stuff that was once on the continent of Antarctica, broke off in about 2020 and was just sort of scooching around, floating around the Southern Ocean. And it just seems to have run aground by South Georgia Island, which is, there's a big British Antarctic survey base there. And this big, huge, giant iceberg just grounded itself. So as that big, giant iceberg, sits there and then melts, and that ice then turns into water, now there's more water in the ocean. And again, some of this has always been going on. Glaciers always split off, which we say calve, add stuff to the ocean. But generally it's been in equilibrium. But what we're at this period now is where actually more stuff is melting than is stuff freezing. And so that's, in effect, we're adding water to the giant bowl of the ocean. And when you add the thermal expansion to that water being added, we very closely match what we've actually observed with the observational data. Make sense? Yay, nay? Yeah, okay, cool. Okay, the other thing to say about this, and we're talking about coastal flooding here, so I'm not going to spend a whole lot of time. This is more the domain of physical oceanography if you guys take that class. But just simply, I want to say that sea level rise is not, and this is another thing the anti-facts, anti-reality people like to say, is they'll find a location where stuff isn't radically changing, and they say, oh yeah, you said that, well, you're so stupid, right? No, the reality is the global ocean is a heterogeneous place. There are issues related to how currents move around, subsurface structures, how the Earth is spinning, all these things. And essentially what that means is, so this now, we're looking at this is some of that satellite data I mentioned to you, right? So the land is blocked out here because there's obviously no water on the land, or no ocean on the land. And so we're just looking at the rest of it. And this is change over about 30 years-ish. What you see is the darker the color, the more that chunk of the ocean, the taller, the higher that chunk of ocean is, and the browner or the more goldeny color, it's actually gone down. If it's white, there's no net change. And so we do see is in some places, like off of Japan and off of sort of just to the west of the Antarctic Peninsula, there's a little bit of decrease. There's a little bit of sort of holing of the ocean, if you will. But the vast majority of the ocean is light blue, and a disappointing amount of it is actually dark blue, right? And so again, that's just to say that this is a heterogeneous thing. We've been super fortunate because of our geography and various other things that here in California, we have relatively minimal sea level rise compared to other parts of the globe. And so again, just like everything else, these disasters play out in an uneven form, right? It's not as if wildfire is a wildfire is a wildfire. It's how that particular wildfire goes through your neighborhood, how that particular wildfire interacts with the winds this month, that kind of stuff. So we're going to just now talk about sea level rise, but it's important for me to make sure you guys understand that it's a messy thing. It's a complicated thing. Okay. One of the first types of flooding, does it make sense? Question so far? Okay. So one of the first types of flooding we have would be considered, that sucks kind of flooding, right? So we would call that nuisance flooding. So that's stuff that doesn't necessarily threaten the hospital, doesn't necessarily, cause life and limb to be threatened, but it messes with stuff, right? It makes the roadbed gets water on it and you can't drive to school, or it takes you an extra, you can't drive as fast as you want to go. You have to go like 5 miles an hour or something through the flood area, that kind of stuff. And that level of nuisance, and so here we're looking at that where we see this little park, right, which has brick and stuff on it and stone. So we're not destroying this. This area is not being destroyed by this flood event, but it means we can't go enjoy that. We can't go have lunch there. Can't walk my dog there. Can't take my significant other on a romantic walk right there. Those kinds of things. So nuisance flooding. Since when I was born, depends on where we are in the world, but is somewhere between 3 times to almost 10 times happening more frequently. So that just background, boring, day in, day out, annoying type of flooding is causing a problem. I also don't want to just completely ignore this, because if you are a hot dog seller or a coastal business and this happens, that's going to mean people aren't going to come get hot dogs. So this is not to say there's no impact. I'm just saying this is not the kill everybody, destroy the city type of impact. There's tremendous change in some areas as well that we can see quite easily. So several years ago, I went on a trip to Alaska, and I'm going actually this summer to Alaska. And my son really wanted to go do that. And I was like, oh, I want to go somewhere else? He's like, no, I want to go. I want to see the difference. I want to see the change in what it looked like a few years ago versus now. And so this is much greater change than what my son and I will see, thank God. But so this is Glacier Bay in the south coast of Alaska. In 1917, and this is what it looks like 20 years ago, right? So it's gotten even fewer. There's even fewer icebergs now. So where, if you're on a cruise ship, where you used to be able to go in, now you go in. I forget, it's like 7 miles farther inland. It was just glaciers, a generation ago. So this is, and this ice is going somewhere, right? This ice isn't just going into the ground. It's into the oceans, etc. So what we're experiencing now worldwide for global sea level rise is about 2 times the background rate of a generation or so ago. Over most of the 20th century, sea level rise was growing at about 1.5 millimeters a year. So the average, and again, we have tides. The tides of water goes up, water goes down. This is the long-term average of that. So the long-term average of that elevation. And so now we're at about 3.6, and I think I need to update. I should probably update this. Now, because we're probably not going to get a whole lot more data coming out of the federal government for the next few years about this, unfortunately. But that's the situation. That's what we're looking at right now. If we talk about how much water is in that frozen component of our water around the Earth, we've increased the melt rate of global glaciers by about 4 times the historic rate. And so this is essentially how much water is melting, is leaving these glaciers. It's a lot. And in particular, the 2 things that we're most worried about are the Antarctic. I mean, there's glaciers all over. There's glaciers in Africa, glaciers in California, glaciers all over the place. But the 2 largest masses that we're worried about are Antarctica, particularly the East Antarctic Shelf glaciers, and then Greenland. And so in the case of Greenland, we've seen a 7-fold increase in the loss rate of frozen stuff. And these numbers are getting quite problematic and quite serious, to the point where some of my oceanographer friends think that essentially the global conveyor belt that moves warm water from the Caribbean and Florida and that area and goes up the East Coast may well already have begun breaking down. And Antarctica is about 4 times the background rate. So Greenland's about 7 times its historic rate. Antarctica is about 4 times its loss rate. Okay, and so what does this mean? So here we go. Here's some predictions As we've talked about, I believe in this class briefly before, but I just want to reiterate it. I think, have we talked about this, or am I not? Maybe I didn't talk to you guys about global climate change predictions. Did we talk about that? Okay, maybe I'm thinking my other class. Okay. So let's just take a look at this. So this is the classic thing you will see as we talk about forecasts for things like coastal flooding in the future, right? So again, the black stuff, the stuff to the left, that is real data. That is what has already happened. That's measured conditions. And again, to orient you, in this case, we're going from the 1800s to 2100, which is the typical. So 2130, 2150, 2075, 21, what did I say? 2030, 2050, 2075, and 2100 are the most common dates, just because they're nice and round and smooth and easy to get our head around. And so you'll see most of the models, for example, go to either 2050 or to 2100. And so the stuff to the left, the leftmost illustration, that is what has happened. That's reality. And then wherever we are now, whenever the model is predicted, it's going to be pretty tight, and the models have gotten quite good, especially over the short term. And so this little gray part is saying where we're mostly deriving sea level measurements primarily from satellites. But this first little bit here, it's more or less the same, right? We're kind of the gray and all these other colors are pretty much on top of each other. That's telling us that the models are pretty much all telling us the same thing. But as we go out farther, what essentially we've done is, just like I mentioned before, the models have all been trained on the black. So the models have all been trained on the past to make sure they can account for everything. So every year when we have a new storm season or new whatever, we tweak the models. We're constantly feeding them. So one of the big worries about the defunding of NOAA is we've made massive progress on improving our forecasts and predictions and all this kind of stuff. We're constantly fixing these models. Many of those folks that were fired last week are the people that developed these models. So they're intentionally having their knees cut off, right? So they cannot add to new data. We cannot improve our models anymore, which seems kind of crazy. It seems like you'd want to know if your cornfield is more likely to be flooded or not, but apparently that's not important to our government at the moment. And so what we're seeing here, it's all the same model. The red, the green, the yellow, the blue, they're all the same model. It's just we're putting in some different assumptions, right? So we're putting in primarily the biggest one, whether there are potentially many, methane emissions, all kinds of. The biggest one is carbon dioxide emissions. Carbon dioxide isn't the most sensitive greenhouse gas, but it's just the numbers game. It's by far the biggest thing. So we have different assumptions, and so those assumptions all come from the political and social realm. They do not come from the scientists. So if we so all these countries have made these commitments to go to solar, go to wind, go to these non-carbon intensive economies, right? And so one of the models, the one that'll be on the bottommost, is assume we do everything. We do every single thing that people said and all the commitments, we totally meet them. Every project we think we might do, we fully fund and it gets enacted and all that kind of stuff. So that's sort of like the best possible scenario, right? As far as we can see it. And then there'll be a range of models in between here and there. And the topmost one will be the one where we assume, for the most part, we assume we're just doing the stuff we're doing. What's actually happening right now with what the policy that our country is pursuing, we're actually not even doing that. We're pulling back on several things. Right? So not everything, the current administration cannot change history, cannot stop. And right now, solar and wind are mostly cheaper than natural gas. And in some places, they're about the same price as natural gas. Way, 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 way cheaper than coal and other more polluting forms. So there's just an inherent, you can't go back too far. However, many of the things we thought were baked in because the law said we were supposed to do this, the current administration is kind of saying, I don't have to follow the law. I don't think I want to do that. And what we're starting to see now is some other high emitting countries are starting to, oh, if the US is not doing that, maybe we don't have to do that either. So it could be worse than this red, but this red is generally, how we go through this process is generally saying, okay, let's just say we don't do any of our commitments, or we just do the minimum amount, the stuff we've already done, we don't add much to that, right? And so you get, and we call these scenarios, and these mostly come from the International Panel on Climate Change, the IPCC. And so those numbers, the scientists aren't calculating those numbers, they're just getting them from the social scientists. They're getting them from the political scientists. So that's what we get. So we end up getting this wide range, and then almost everybody, what they do is they look at this and they go, red is too scary. Literally is what they do. Red is too scary. That seems too scary for me. Let's not do the too scary. And they go, the blue, in this case, the lowest of the blue, that's really optimistic. I don't think we're going to be able to do that. And that is literally how everybody has approached this. It's like, okay, so let's do something in the middle, right? Because that seems sort of reasonable, right? It's not a mathematical calculation, whatever, but usually, so the computer modeling of sea level rise and everything else is all these things, right? So this is this scenario, that scenario, that scenario, that scenario, that scenario. And then we take what's known as the consensus model. And so that'll be something in the middle. And that's what policymakers usually use. So those tools that you'll look at later today, or if you don't get to it today, this evening or tomorrow, whenever, those models that you're going to use, all the data that you see are going to be using predictions of the middle of this range of sea level rise. And so I'll just say it again because I think it's really important to say, this is the NOAA modeling, okay? The NOAA data center that's doing this is being defunded, the computer center that runs these models. These are very hard to run models. It would blow your computer up, right? So we need like supercomputer like stuff, or Amazon Web Services type of computing power. So there are various ones around the world, and they work, some are more conservative, some are more liberal. Some tend to come out more towards the blue side of things. Some tend to come out more towards the red side of things. And so when we calculate these emission scenarios, we pull all of them together. Again, the stuff that's in the middle is the consensus model. The stuff in the middle is what everyone agrees to, what Vladimir Putin agreed to, what the country of India agreed to. So people that aren't really big into the climate change dealing with world, they all agree that's a reasonable model, right? And so when we make all of our predictions in terms of the sea level rise that we suck into our other policy models or legal guidance or whatever is always in the middle. There are models that are much more aggressive. So like this red one, right? That we've basically not picked for judgment call reasons. But some of our models, like one of the ones that runs out of Scripps, actually shows a lot of like a steep curve. So just because we have these modeling and we have all the newspapers talk about this and all the politicians, that's not a guarantee that is really how it's going to play out, right? It could actually be much more scary than that. It could also be less scary. Hopefully it'll be less scary. But the point is we have to use something. And so what people tend to use is they tend to use the middle part, and we do not add noise. We do not add, if you guys are in my data viz class or our class, we always talk about the central tendency and the variation. There's almost never variation when it comes to the policy. It's just sea level rise is going to be X number of feet, period, end of story. Okay, so for us, how that manifests for us here in California is we now legally, anybody doing anything in the coast of California, you must deal with climate change. You can't ignore that it's happening. And specifically in the context of our class today, coastal flooding, you must deal with sea level rise. You have to deal with sea level rise. And so the guidance here is from one of those consensus models from about 12 years ago, whenever it was, is about the average height of the ocean will be 3.5 feet higher than basically the year 2000. So I'll just say that. That's 3.5 feet higher on average, day in, day out, midnight, noon, winter, summer, whatever. That is not adding on king tide. That is not adding on storm surge. That's just the background level of the ocean. That is, and pretty much when this was being passed, a lot of us were like, yeah, that doesn't seem right. And they're like, that's what we could get passed. But that's the law. So legally, if you're going to propose to put a bridge in, or you're going to fix your house or whatever, you have to assume is going to be, more than a meter of sea level rise. Pretty much though, what most people are now going to use is 7 feet. So about twice that. And so you don't have to, but it's the strong recommendation of some state folks that you actually do use 7 foot, right? So that's taller than me, right? That's a radical change. That is almost assuredly way too low. That's almost way too low. This starts to leave the area of science and gets into policy and how do we enact change. If we tell people that the giant boulder is coming down and kill everybody, you're like, okay, screw it, I'm just going to drink all night, right? So there's some thought that, well, you tell people a smaller boulder is coming and we need to sort of run to get out of the way of that smaller boulder, with the hope that once you start to run, you go, you know what, dude, you got to run a lot faster, right? And so that's sort of the psychology of this. But regardless, legally, California, we have to plan for 3.5 feet of sea level rise, but the strong suggestion is to plan for at least 7 feet by 2100. 2100 has a little bit of the same problems we were talking about the 100-year flood, right? You guys with me on that? Seems kind of far away, like 2100, dude. Maybe I'll have a house by then. Maybe I'll be able to pay for a house by then or something, right? So it seems like forever away. Seems like forever away. And so one of the dangers, obviously, this is real. You saw the models, but sometimes putting off the number so far away can also lead some people to think, not you, of course, you guys are educated, but simply like, oh, well, it's going to suddenly be a step function. It's not going to change very much, then 2100 is going to change a lot. So that's a issue as well. Okay, all of our climate models, all 100% of them, are suggesting that the average temperature is going up, sea level is going up planet-wide. We're also starting to see, we have seen and are continuing to see, and we predict to see, I was just in a workshop today about this, changed sand supply. So in our part of the world, in Southern California, where we're about 80% of our coastline is sandy beaches, that sand builds up. Sand's a dynamic thing. It goes in sometimes parts of the year. It goes offshore sometimes of the year. It gets washed away and new sand comes in. By messing with our rivers, by damming all of our rivers and things of that nature, we actually make less likely that sand can come into the system, which is a natural buffer, right? So if we have the sea level rising and we have more sand coming in, the ground can just go a little bit higher, right? And that is being compromised. We're changing the hydrological cycle in terms of rainfall events and stuff like that, which is influencing erosion, et cetera. We're seeing a dramatic increase in atmospheric rivers, that's where the huge amount of water, we used to call them pineapple expresses back when I was your age, but basically, huge amount of rain and rainfall over a very short period of time. And so while that's great to get all that rain for our crops and for our reservoirs, that much rain that fast mostly cannot percolate into the soil fast enough. So usually much of that translates as flood events into our channels, et cetera. And then we have various alteration of the organisms, the biological organisms that can help us deal with climate change. So things like Phragmatopoma and oysters and things of these invertebrates and stuff that live on or near the coast that can help cement rocks and things like that together to add sort of armoring, coastal protection, or help accumulate sediment themselves and act like sand traps, and so be little like buffers, speed bumps to the waves coming in, etc. Most of those organisms are under serious assault because of climate change, primarily because of increased ocean acidification, which is making it very, very difficult for some of the form of calcium that's when the larvae is floating around in the ocean and then starting to crystallize, lay down its shell. That form of laying down of calcium carbonate is very pH sensitive, and so as we make the oceans more acidic, in many cases that can't happen, or it can't happen at the rate it normally has. So we're seeing a lot of critters have problems essentially surviving to adulthood. And then nextly, we have a lot of also associated with climate change, increasing numbers of marine heat waves. And so those things are more likely to kill critters by thermally stressing them. So all these things are coming together to make it a more coastal, floody world. Questions? Okay. Yeah, we guys know about tides. We'll skip that. All these things sort of can influence. As I mentioned, we have daily tides, and as the sea level rise just goes up, 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 we can get to the point where even just regular daily tides become more like routine nuisance tides. But they typically aren't like, again, mortality or anything like that, but they cause problems. King tides, as I mentioned, that's that seasonal peak in the highest of the high tides. That is a particularly problematic one. And in fact, we used a lot of this from a research context. We use a lot of this for citizen science projects to sort of say, hey, what will it be like when the tide is a foot or two, or when the sea level is a foot or two higher? So king tides are a nice physical model for that. So you can just walk out and take a picture of how many streets are flooded in Oxnard or whatever. And you don't need any fancy modeling. You're just like, oh, if the water is this high, these are the parts that flood. El Nino, as we mentioned before, is going to make things crazy. And then where we really see the problem and most damage, loss of human life and costliness, is when these other things are going on, and then you layer on top of that a coastal storm. So I'm going to play 3 videos, then maybe we'll take a little break here. So it's sort of short, but I think they're illustrative of this flooding stuff. So let's see if we can hear these.
You're good to go. It's hard to name a thing in this lifetime that'll last me a lifetime, but I'll only need one.
Key Largo neighborhood are dealing with a flood of problems.
Streets have been underwater for more than a month, and families are fed up. Local 10 News reporter Hatzel Bella joins us live. Hatzel, what's the solution to all this?
Well, that's a solution that they're still trying to figure out the solution between the county and residents who live here. Short-term, long-term, they still don't know. But I can tell you, this water that's been lingering here for 45 days, some residents say, keeps them from leaving their homes, and they're simply frustrated. It is fall in Key Largo, months where residents expect flooding, but not for this long.
Today is day 45.
This is the new normal, it seems. So 45 days, I can't imagine.
No.
Emily Stewart gives us a tour of the Still Right Point subdivision.
This is probably one of the deepest parts of the flooding.
There's about 215 homes here. It is surrounded by canals between US 1 and the Florida Bay.
That's become the way of life that all of us feel like we're hostaged in here.
Our hurricane specialist, Brian Norcross, explains why it's happening.
We had a huge Hurricane Lorenzo, which was pushing back on the Gulf Stream, kind of slowed it down. That means the Gulf Stream waters that are right near the Keys pile up, and the water has to go somewhere.
He says the tide has been running nearly 1.5 feet above normal.
The perfect storm.
Trips outside the neighborhood are pre-planned. Folks who live here want to lessen the possible damage to their cars from the seawater. George Smythe has to wash his car daily, fearful the salt water will rust and destroy it. We met with several residents who say Monroe County hasn't done enough since they started addressing the issue in 2012.
The cost-effective solution would be just basically to raise the road up by putting asphalt on it.
Monroe County officials say there really isn't a short-term solution aside from storm drain enhancements and cleaning. They want a long-term fix.
So right now, we're doing a $4.7 million study to know exactly how bad the problem is and what needs to be done to fix the problem.
Back out live, you can see some residents washing their cars after driving through the salt water. This is even affecting law enforcement. That's because Monroe County Sheriff's telling us that they're not doing routine patrol because they're fearful of what damages the water will cause to their vehicles. They are still, of course, doing emergency calls if that were the case here in this neighborhood. For now, reporting live in Key Largo, I'm Hatzel Vela, Local 10 News.
Extremely dangerous Hurricane Florence continues to close in on the southeastern United States, and it will carry with it significant storm surge and life-threatening inundation. Let's look at these maps, for example, created by the National Hurricane Center to give us almost a block-by-block assessment of how much water rise you can expect above normally dry ground. This, for example, over southeastern North Carolina in Beaufort and Morehead City. These are some locations that we think will get significant storm surge. Now, these areas shaded in yellow and orange can expect water rises of 6, maybe even 9 feet. That's going to flood many of these locations downtown. But it's more than that, because this is not just going to be a coastal phenomenon. We know that the storm surge with Florence is going to continue inland and surge many miles. For example, in Newport, North Carolina, significant inundation, water rises above 9 feet nearby, and even farther west than that, this storm surge will find its way well inland. So let's now have a look at what that might be like. For example, we know Florence is going to bring 1 to 3 feet of inundation across many locations. That certainly is enough to knock you off your feet. It can definitely stall cars out and even carry cars away, and certainly flood many of the lower levels of structures. But we know Florence is also going to bring water rises well above that, perhaps up to 6 feet. Now, 6 feet of water, imagine that. That carries large objects in it, like cars, for example, that can act like battering rams and enhance the damage that would otherwise be. And also, we know that can flood the lower levels of many structures. We also know that Florence is going to carry with it likely storm surge well above that, perhaps 9 or 10 feet, maybe more. That will totally cover up one-story buildings and structures, leaving them underwater, and certainly pose a risk to many. There are very few places that are safe where the water rises this high. So please, follow the advice of your local officials and heed the evacuation warnings, and of course stay updated on all the latest forecasts.
So a different way to...
From about 1993 to 2010, off the west coast of the United States, we've seen about 0 sea level rise or even negative sea level rise, so sea level was falling during that time period. But since about 2010, 2011, we've seen this really rapid increase in sea level off the U.S. West Coast. We're seeing this recovery back towards the global mean. And if this continues to increase, then you'd expect to start to see sea level impacts associated with this increase. Increased coastal erosion, increased high tide flooding, these kinds of things as sea level continues to increase. So there's a number of things happening. One is there's this background increase in sea level associated with global warming, thermal expansion, and the melting of ice, which is impacting sea level along the west coast. That's causing this long-term increase. But on top of that increase, there's this oscillation that occurs, and actually a number of oscillations. So the Pacific Decadal Oscillation is one of those. The El Nino Southern Oscillation is another. The Pacific Decadal Oscillation is a large-scale climate signal centered in the Pacific Ocean. Every 10 years, we see this shift in the sea level between what we see in the Western Pacific and what we see in the Eastern Pacific. And these oscillations suppress or elevate sea level over different time periods and really either exacerbate or diminish the effects of that long-term sea level. Since about 2010, 2011, we've been seeing this shift in that decadal variability associated with the Pacific Decadal Oscillation. And what that's doing is causing sea level along the west coast of the U.S. to go up. So really high rates of sea level causing sea level to shift very dramatically, and this increase that we've been seeing in the satellite records and also in some of the tide gauge records along the U.S. coast as well. Sea level is going to change in how it's going to impact the coast, I think is really important so we can inform people, they can make good decisions for their future, and we can start to adapt and adjust our way of living in order to account for these effects that are going to occur in the future.
Okay, so just to finish up, right, we can have more or less problematic situations as this plays out. Just about everywhere in coastal California is impacted by the road closures, so PCH or residential streets. As we have more and more frequency of sea level rise. Another key one is that our stormwater systems are very frequently being overridden, right? And so that means that this is normally where the water exits our system and dumps into the ocean, but with sea level rise, it's essentially reversed. So we can see water coming out of manhole covers and things like that, sometimes very, depending on the system, very far inland, relatively speaking, potentially miles inland. And then a lot of damage to infrastructure. This is where a lot of the concern has been directed. When we do have a formal federal disaster declared, if this coastal flooding was to the extent that it caused several problems, maybe we'd be a federal disaster area. Historically, when FEMA came in, they would say, no, we're not going to fix, for example, your infrastructure. We're not going to fix your water system or your storm drain system. Why? Because you had a screwed up system to begin with. And we're only going to recover the infrastructure to the level it was before the disaster. We're not going to make it more sustainable, more resilient, right? I guess that sort of makes sense from a moral argument. You're like, oh, well, I don't want people to benefit from having a disaster, I guess. But if you lived in a society where you're trying to be better, one might think that in actuality, maybe we should make it more resilient. Maybe it flooded partly because we had this old system from 100 years ago. Maybe we should take this opportunity now that it's broken and we have to go in anyway, right? So it's expensive to fix these systems. Totally agreed. But if it's already broken and we already have to, dig up the concrete, jackhammer the whatever, get the people in there, hey, maybe we go and make it nice. So we did have that directive for a while. Unfortunately, the current administration, the first Trump administration reversed that and said, no, you can't make anything more resilient. And then it was reversed again with the subsequent administration, and now that the Trump administration is back in power, they've gone back to, you can't make things better. You can't make things more resilient. We're not going to pay for you. You got to go figure it out yourself. And so much of the conversation revolves around public infrastructure, right? Power plants, water treatment or sewage treatment plants, water, that kind of stuff. And then another big one here is just the erosion. So there's the actual water itself, which is obviously instantly problematic. All of a sudden now we have water in our rooms or in our structures. But over a period of time, if that happens, we tend to see significant erosion, so significant removal of the sediment and other things. And so even if it's not going to flood next week, your foundation to your house might be weakened or something of that nature. Those are the main ones that we're worried about with these flooding events. And I just shared these links with you guys. You guys can check them out when you come back from break if you're so interested. But these are just a few examples of some tools you can use to explore sea level rise and what might be going on with those. So the NOAA tool is maybe it'll work, maybe it won't. Maybe it's working now, maybe it's not going to work in a month or two or three or whatever. But the other two are independent of the federal government. So the other two will almost assuredly still work. The difference there being is that the NOAA one historically has been frequently updated. It is refreshed as we get new data. These other two efforts, the Nature Conservancy, I was part of the first one of these, which was here in Ventura County. But those are using sort of older data. So they're still useful and still helpful, but they're using modeling data from several years ago, 5, 6, 7 years ago. And the Climate Central is also using some not quite as old but historic data. So the bottom two are not being updated in real time. The upper one isn't being updated in real time, but historically it was updated fairly frequently. So you guys can play with those when you want. So why don't we take a 10-minute break, and I will see you guys when you come back.